Today we will be discussing nuclear magnetic resonance spectrometry. NMR utilizes magnetic nuclei and their known responses to the presence of an external magnetic field to determine the structure, reaction state, and chemical environment of the sample. The sample is sealed in an NMR tube and placed in the sample holder located in the center of the machine. When a homogeneous magnetic field B0 is introduced, the nucleus becomes polarized based on their spin states. Then current carries electromagnetic frequency through coils and around the sample, inducing a magnetic field B1, causing the nuclei in the sample to align themselves with or against the magnetic field. As external field is removed, excited nuclei relax back to the ground state. Their absorbed radio frequency energy is emitted at the same frequency and is transmitted back to the detector, where it amplifies the intensity before it's converted to NMR peaks on the recorder. Consider magnets as nuclei orientations. Before the nuclei are placed in the magnetic field, they have random orientation. In the presence of an applied magnetic field, the nuclei will either align with the external magnetic field in the alpha orientation, where the north pole of the nucleus aligns with the south pole of the magnet, or align against the field in beta orientation, where the north pole of the nucleus is aligned with the north pole of the magnet. When the nuclear magnetic moment associated with a nuclear spin is placed in an external magnetic field, different spin states have different magnetic potential energies. The energy gap is the energy of relaxation when the nuclei returns to ground state. The emitted radio frequency is directly proportional to the strength of the applied field. Radio waves are sufficient to induce the transition that are very low in energy and frequency. The following equation shows the energy difference in spin states. The radio frequency pulse generated during the nuclei transition creates a free induction decay graph of varied magnetization with time. Then a Fourier transform is performed in order to reveal the frequency component and produce a frequency versus intensity NMR spectrum. NMR samples are prepared in the following way. A solvent is chosen, the sample is dissolved in the solvent, and the mixture is filtered to remove any remaining particulates. Lastly, the mixture is transferred to the NMR tube. Solvent choice is dependent on the following: solubility, choose a solvent that can fully dissolve the sample; solvent viscosity, where less viscous materials increase the resolution and collection time; cost, the most versatile and economical solvents are deuterium oxide and chloroform; and overlapping signal peaks. Ensure that the peaks of the sample do not overlap with that of the solvent. In NMR proton detection, 2 to 10 milligrams of the sample is dissolved into 0.6 to 1 milliliter of solvent. In high molecular weight samples, increasing sample concentration reduces signal-to-noise ratio. Carbon-13 detection is 6,000 times less sensitive than proton detection. Therefore, sample concentration increases until solubility limit of 0.7 milliliters solvent is reached, approximately 10 to 50 milligrams of sample. High frequency, 500 to 600 MHz, is used to reduce the collection time in highly concentrated samples. The sample mixture is then put in a 5 mm diameter and 20 cm long NMR tube and sealed with a stopper. The mixture should be 4.5 to 5 centimeters in height and will have an interaction volume of 0.9 to 1 milliliter. Frank Bove pioneered NMR and discovered its ability to characterize polymer structure, microstructure, and composition of material. Recent improvements in automation, sensitivity, and resolution have led to NMR usage for discovery, design, and characterizing biotech drugs. Additionally, NMR is used to examine the structure of proteins and RNA. NMR spectroscopy is limited by molecular and protein size. It is difficult to analyze larger molecules because of reduced signal sensitivity. It's an expensive spectrometry method. The data is more difficult to interpret in larger proteins and therefore not recommended for proteins greater than 25 kilodaltons. NMR sensitivity for food is much lower than high-performance liquid and gas chromatography methods.